Okay, so in this video we're finishing this question. We started in the last video where we started with a triangle, wrote the equation for each side, found the midpoint. Now we're going to finish up. We're going to find the perpendicular bisectors, and then we're going to think critically about what's happening here. So as I said in the last video, to find the perpendicular bisector of the equation of each side, we really just follow two steps. One, find the negative reciprocal of each slope. That'll give you a perpendicular line. And then make sure you know the b value of your equation. And this means you're going to find where the perpendicular bisector crosses. And that'll give you an equation, right? The slope and the y-intercept. But really, I mean, if we look at the picture here, and let's do a rough sketch of this. Here on this side, right, a perpendicular bisector will do two things. It'll cross this side AC at a right angle, and it'll bisect it. That means it cuts it in half. So it'll almost go like this right here. Let me fix that. Right? So this is the perpendicular bisector. It's still not a good drawing, sorry. That's a little bit better. The perpendicular bisector of this line. And it's going to cross the midpoint. It's just a little bit off. I'm not happy with this drawing here. Let's try one more time. One more time. There, it's okay. It's probably the best I can get it. So that's crossing at a 90-degree angle, and it's crossing through the midpoint. That's going to help us. The same thing with this line right here, crossing at a right angle, right, and crossing through the midpoint. And the same thing with this line right here. It's going to cross through at a right angle at a midpoint. And you can see, you know, even by estimation, we can verify this in a moment, but they're all going to cross here at this point, which is the midpoint of the side AB, which is a nice feature. And this is what we're going to call point Q in this problem. So these red lines are our perpendicular bisectors, and the things we know about them are that they cross these line segments at the midpoint because they're bisecting, and they're perpendicular to each segment. So that's actually kind of easy to deal with. So all you have to do now, we write down our three original segments. We have AB, BC, and AC. And then we'll write their perpendicular bisectors next to them. So let's write these out. For, we'll start with AC, why not? AC. For that we have originally y equals 1/2, right? 1/2 x. And then our y-intercept was 4.5, so plus 9 over 2, or 4.5. And to get the perpendicular bisector, all we have to do is take the negative reciprocal of the slope. That's something we cover in other videos. So negative 2 over 1, or negative 2, x. And the y-intercept, right, again, here's the line right here. It crosses the midpoint, which happens to be at the y-intercept, right? 0 and then 4.5. So this equation of this line will be just negative 2x plus 9 over 2. And that's this line right here. So I'll write that in. So y equals, and then you can write this any way you want. I'm just going to try and color code that helps me keep track. Negative 2x, right, plus 9 over 2. Sorry with the sloppy handwriting. This program is running a little slow. So it's plus 9 over 2. Fix that. 9 over 2. And that's this line right here. Okay, so next we have, let's do AB next. So for AB, originally our equation for AB is getting a little messy now, is 3x minus 3. So that's our original equation. Y equals 3x minus 3. And now, I mean, the slope is just a negative reciprocal, so it's negative 1/3 x. Oops, negative 1/3 x. And here, the only trick is to get the y-intercept. You have to remember that this line is crossing through. Well, here's the line right here, sorry. It's going to cross through this point 1.5, 1.5. So we don't know the y-intercept yet, but we can quickly figure it out. All we have to do is say, okay, if we know the equation is going to say y equals negative 1/3 x plus something, well, we know that it has to cross this point, 1.5, 1.5. So let's plug that in. So x is equal to 1.5, so negative 1/3 times 1.5, which is 3/2, right? That's the same thing as 1.5. plus something, some unknown y-intercept, should give us the y value we need here, which is also 1.5, or 3.5. So now we just solve here, and that'll give us the y-intercept. So this cancels out, right? 3 over 3 is 1. This is negative 1/2, plus b is equal to 3 over 2. Solving for b, we add 1/2 to both sides, and that, if we think of a half plus 3/2, it's 4/2, or 2. So the y-intercept of this, right, of this line is 2. And I almost drew it accurately. Here it's crossing at 2. So that's the equation for this line right here. This perpendicular bisector, y equals negative 1/3, sorry, it's all over the place now, plus 2. And you can, I hope it looks better on your graph, plus 2. And then we have one more to go. And we're almost there. Hang in there, we're almost there. So AC is next. And AC originally, oh, I'm sorry, we've done AC already. We've done AB, we've done AC. Now let's let this BC, our last side. So BC. BC, right over here, and here's our line, is going to be the perpendicular bisector here. Will have a negative reciprocal of our original line, which is y equals negative 2x. This is the line right here, the blue line, minus 3. Now the negative reciprocal will be positive, not negative, 1/2 x. And then again, we need to find the y-intercept. So we don't know what it is, but we know it has to cross this point, negative 1.50. So let's plug that in. So x is negative 1.5, or negative 3/2, times 1/2, our slope, right? Plus something should give us what? Well, this point is 0, right? So plus something should give 0. So we scroll down a little bit. Here if we multiply these two fractions, we get negative 3 over 4, right? Plus something equals 0. Well, what do I have to add to negative 3/4 to get 0? Well, the answer is positive 3/4. So here b is equal to 3 over 4. And that gives us our final equation. So believe it or not, as messy as all this is, we finally have our 3 equations. And here's the third one over here. Y equals, I'll just write 1/2, because I'm running out of room, 1/2 x plus 3/4. 1/2 x plus 3/4. Now we have our 3 perpendicular bisectors with those equations. And what's next? Well, this is where things I think get interesting. Here we choose 2 of any of the 3 equations and solve the system of equations for the point where these 2 perpendicular bisectors intersect, which is Q. Now from our picture, we can already tell that they've got to meet at this point here, or about that point. So we can pick any 2 of the lines. They'll all meet there. But for 2 of them, right, if we say when are they equal, when do they cross each other, when are they the exact same thing, well, set any 2 equal and we'll get the x value of this point. And then we can use that x value to find the y value, to find exactly where this is happening. So again, I can choose any of the perpendicular bisectors, anything I want. I'm just going to choose, I'll choose AB and BC and set them equal. So here we go. So let's say the perpendicular bisector, I'll write this, the perpendicular bisector of AB equals the perpendicular bisector of BC. And I think I have the right equations there. So now that means I have negative 1/3. All I'm doing now is setting up an equation here. So here's the perpendicular bisector, AB, negative 1/3 x plus 2. And that equals what? Well, BC was 1/2 x plus 3/4. So 1/2 x plus 3/4. Alright, so now we just solve for x, and that'll give us the x value of where these points meet. So, okay, of course, many ways to do this. I'll add 1/3 to both sides and subtract 3/4 from both sides at once. So I'm going to add this to both sides and add this to both sides. So then I get 2 minus, I'm going to add 1/3 to both sides but subtract 3/4 from both sides. So 2 minus 3/4, what's that? Well, I'll write 2 as 8 over 4, right? And then minus 3/4. And that'll be easier to deal with. 8 over 4 is 2. Now adding a third to both sides, I'm adding a half x plus a third, and I'll write those in terms of sixths. So a half is 3 out of 6, plus a third, which is 2 out of 6, right? And this is all in terms of x. Alright, so now what happens? Well, 8 fourths minus 3 fourths is what? That's 5 fourths. And 3 sixths plus 2 sixths is 5 sixths. And that's x. So 5 sixths x equals 5 fourths. Last step, I'm going to multiply both sides by 6 fifths, or 6 over 5. So then what happens is I get 6 over 5 times 5 over 4. Oops, 5 over 4. And I know this looks nasty, but you'll see how actually nice and neat this really is. Now that equals x. I got rid of the 5 sixths x by multiplying by the reciprocal, 6 fifths, which made it 1, so it's not there anymore. And this equals what? Well, it equals 30 over 20, right? Because 5 times 4 is 20. And if we reduce that, 30 over 20, we get 3 over 2, which is really 1/2, and that equals x, which is exactly what we'd expect for point Q. Looking at this terrible diagram, point Q is the midpoint of AB, so the x value is 1.5. So now to find the y value, we take this x value and plug it into any of the equations that we want to. Right? We have choices here. We can do anything, but I'll just plug it into BC. So B, the perpendicular bisector BC. So that's this equation right here, 1/2 x plus 3 fourths. So x is 3 over 2. So 1/2 times 3 over 2. Oops, sorry about that again. 3 over 2 plus 3 fourths. And if we simplify this, what do we get? Well, you can go through it and you'll get 3 over 2. And that's our y value, right? Because we plug this x in, that gives us the y. So that means our coordinate q, that's what we're doing right here, has to be 1.5, comma 1.5. And that is the midpoint right here of AB. So it turns out that these three lines, these perpendicular bisectors, meet at the midpoint on this side. Pretty cool stuff. And that means a couple of things. Now this only happens, right? And I guess there's a lot to talk about here, but this only happens when you have a right triangle. The perpendicular bisectors of each side will meet at the midpoint of the other side, right? If it's a right triangle. That's what's happening here. So that's part of the interesting properties of this triangle. But before we even get to that, let's answer G, because this is where I think things get really awesome. They want us to find the distance from Q to each vertex of the triangle. What do you notice? Okay, so basically we're going to apply the distance formula. We're going to look at distances from Q, right, to each of the vertices. So let me see if I can set this up. So now we know a little bit more. We know that this is Q over here. The midpoint here is also Q. So all we have to do is set up our distance formula. How far is it from here, right, to this vertice? How far is it from here to this vertice? And how far is it from here to this vertice? Now, the distance formula, right, all you're doing with the distance formula is applying the Pythagorean theorem, which is also great because we have a right triangle here. And it says that basically you take the square root of delta x squared, the difference of the x values squared, plus the difference of the y values squared. And you could write x2 minus x1 or you know, y2 minus y1, but delta y, delta x will suffice. That's perfectly fine. So, and what this tells me, since we're adding these two, it can appear in any order. And it could be delta y squared plus delta x squared, it doesn't really matter. So let's get started. So I'm going to set up the three formulas, and without solving, I think we'll see something. So the distance from Q to A, so Q to A, what's that? Well, that's going to be delta x, so 1.5 minus 3, 1.5 minus 3 squared, plus the delta y squared, so 1.5, right, minus 6, so 1.5 minus 3, and 1.5 minus 6 squared. Oops, fix that. 1.5 minus 6 squared. And the distance formula, we'll find the square root of that. So that's QA. Now let's find the distance, without even calculating yet, to QB. And that's from here to here. So now, square root delta x, so 1.5 minus 0. So that's 1.5 squared. And then delta y, 1.5 minus negative 3. So plus, right, 1.5 minus negative 3, which is really 1.5 plus 3 squared. And then one more, you might already see something, QC. Well, same strategy, 1.5 minus negative 3. So 1.5 minus negative 3, that's 1.5 plus 3 squared, and I don't know if you noticed anything yet. And then 1.5 minus 3 squared. Okay. So before we solve, we'll pick one of these to solve. We should notice something. We should notice that these are all identical. How do I know that? Well, here, let's start with this one. We have 1.5 squared. In each of these, do we have that? Absolutely, right? Or something, well, that's going to be the same. Here, what's 1.5 minus 3? That's negative 1.5, but it's being squared. So you should know, I think, that 1.5 squared plus negative 1.5 squared will be equivalent, right? A negative number and a positive number, they're the same absolute value. When you square them, you get the same number, which is, in this case, 2.25. Oops, 2.25. Right? Okay, so that's in these two. Is it here as well? Yes, it's right here. And so what? It's second. We're adding. The order doesn't matter. What about the other one? Well, in each of these, 1.5 minus 6, 1.5 plus 3, and 1.5 plus 3, they all equal either 4.5 squared, right, or negative 4.5 squared. What does that equal? Well, I know that 45 squared, I can think of 40 times 50, which is 2,000, right? Isn't it? No. Yes, 2,000 plus 25, so it's 2,025. I think it's 20.25. But let me just check on the calculator. This is 4.5 squared. Oops. So 4.5 times 4.5. Yes, 20.25. So these are all going to be the same distance from Q. Okay, so what is that distance? Let's just finish this. So we want to add these two, and we get 22.5, and then we take the square root of that. So the square root of 22.5, which is between, right, 4 and 5. It's decimal, because 4 squared is 16, 5 squared 25, but I'll leave it at that. So the distance from Q to any of these vertices is the square root of 22.5. It's a little bit longer than 4, but pretty close to 5. So it's between 4 and 5. I should say it's closer to 5. Why is this awesome? Well, because this is a really important concept. This is a certain type of center of a triangle. Believe it or not, this Q right here is the center of this triangle. If you consider the center what's called a circumcenter. There are many different types of centers, and I really encourage you to really dive in and think about what that might mean to have a different center. For example, a centroid is a center where the triangle is balanced. So like if this was a piece of metal and you're trying to balance this metal triangle on a stick, where would you put the stick to balance it? Well, that would be the centroid, right, some point in here. But here we have a center because it's where all of our perpendicular bisectors are meeting. It's called a circumcenter. And what's so special about the circumcenter is what you're kind of showing here. The distance, right, from the circumcenter to any of the three vertices is the same. So you can almost think of this, you can almost think of this distance right here as a radius. And that's something else that pops up in this question called the circle. It's one word, circumcircle. What is that? Well, it's a circle, right, with the origin at the circumcenter. And what does that mean? That just means that this is the center of the circle, right? And if you draw that circle, it'll pass through, let me use a different pen here, because I think this is so cool. It'll pass through our three vertices. And this program is running slow, and my circle's Definitely not the best, but there we go. So you can see that, or imagine that if my drawing was much better, if you draw a circle with the circumcenter at the middle, right, that circle goes through the 3 vertices. And that makes sense because the distance from the circumcenter to the vertices is the same. It's the radius. So it brings up these 2 great ideas in centers of triangles. And we're definitely done with the problem, right? We found that distance. But H, right, is just labeling everything, and I feel like we've already taken care of that. All right, so I hope you enjoyed. This is a 2-part video. Long problem, had some real challenges, but I hope you enjoyed it. Thanks.